All right, we should get started because we have so little time today for Jenny to tell us about all her great science. So Jenny is visiting us from Princeton. You might recognize her from 10 or 12 years ago when she was a PhD student at Harvard after doing a bachelor's degree at Yale. So today, Jenny is going to be telling us about going wide and deep with the Hypersuprime Cam. And Jenny, take it away.
Thank you. It's always fabulous to be here. Since I was last here, I had a baby, so that's the biggest event in my life. She's now 9 months old. And we have wonderful new results from the Hypersuprime Camera Survey, so I'm super excited to share some of those with you. I will tell you, I shouldn't publicize this, but we started thinking about HSC when I was a postdoc at Princeton, and we like to refer to it as the Hypersuprime waste of time. And I'm pleased to report that we were totally wrong. It's just been incredibly rich to work with these data, and we're having a great time. When I put this talk together, I had 4 parts because all these projects were just starting, but now people have been working really hard. So I suspect I'll only get through 2 of these projects today. The Searching for Low Surface Brightness Galaxies, this is work my finishing graduate student Johnny Greco has been leading. He's on his way to be an NSF fellow at CCAP. So keep an eye on him. He's doing fabulous work. And then a new student, Aaron Cato-Fogg, who's been looking for low surface brightness tidal features around massive galaxies and seeing what they can tell us about the merger histories of galaxies. I won't get to the halos, the outer parts of central brightest cluster galaxies today, but I think Song was probably here recently. And then if there's time, my postdoc Andy Goulding has been thinking about what are the mechanisms that trigger luminous AGN activity and whether we can finally definitively tie merger activity with accretion onto supermassive black holes. Probably I won't get there, but you should invite Andy back. He loves to come to CFA and tell you about himself. As you can see, the theme is really that a very wide and very deep imaging survey can tell us a lot about the low surface brightness universe, which in turn can inform our understanding of galaxy evolution. So this is part of a large 2-part survey that we're undertaking at Princeton in collaboration with the astronomical community of Japan. The first part was the Hypersuprime camera, which is now taking superb images of the sky. The second component will be the prime focus spectrograph, which we're still building, and we hope that that second survey will start in 2020. And together, this project is called Sumire. That's Japanese for violet, so there you go. Here is the Subaru Telescope in Hawaii. I'm sure you're all very familiar with this mountain, this Mauna Kea. And as you probably know, if you've ever been to Subaru, or even if you haven't, it's a kind of monstrous telescope, and it's one of the only ones with a prime focus instrument, so we have a very wide field of view, perfect for doing surveys, and that's of course what we do at Princeton. This is the fields on the sky of the HSC survey. I don't expect it to mean anything to you, but if you're one of those people who has multi-wavelength maps in your brain, here are where all the HSC fields are. It's a wedding cake survey, so the wide area, which is what I'll be talking about today, this is not working very well, is 1,400 square degrees ultimately to a depth of 26, the deep component 30 square degrees, and some narrow bands. One of the things the Japanese excel at is finding Lyman alpha emitters. So that's what the narrowband survey is for, and then a stupidly deep component, which we may or may not ever achieve those depths, 28. That's to see the first galaxies. So that's the overview, and today I'll really be focusing on results from wide, and specifically the first 200 square degrees of wide. Just for context, you have to show the parameter space that we push into. So there's wide compared to Sloan, right? So we are both considerably deeper than Sloan, and we have really half arc second PSF uniformly across the field. So this enables quite a lot of new science. Got to compare your survey to the full moon. So there's the full moon, and there is the 1.8 square degree field view of HSC. All right, so there's a lot you can do. Here's our sort of publicity image. This is like a 2-minute integration of Andromeda, and that's all the fields that Julianne used to study Andromeda with FAT. Each of those squares is many, many HST pointings. So of course we don't get the resolution of HST, but we do get quite a dramatically large field of view, perfect for this kind of surveying of the universe. And then our favorite game always is to compare HSC and Sloan images for the same objects. So you can see just the incredible structure that we can see in massive galaxies and their outer parts, and in dwarf galaxies that you might only marginally detect in Sloan. Suddenly you can see their H2 regions and so on with HSC. And on the right, just showing off the fact that the PSF is really remarkably stable across the whole field of view, which is quite a triumph of the optics of HSC. So it's really enabling quite a lot of science. Okay, so let me jump right in now with the low surface brightness galaxies. And of course, this was sort of sparked by work that Peter did with his Dragonfly survey. These galaxies are all to scale, so we have Andromeda, the Sombrero Galaxy, and then these crazy galaxies that are comparable in size to the Milky Way, but only harbor maybe 10 to the 8 solar masses in stars. We've known about low surface brightness galaxies for a long time, and in fact they were very popular to study in the 90s. So Peter really sort of regenerated our interest in this low surface brightness universe. The angle that I'd like to push today is that actually dwarf galaxies are one of our strongest ways of testing lambda CDM because they are so dark matter dominated. But of course, until we probe surface brightnesses like this, we don't know what we're missing. And so this is really, I think, a crucial window into questions like too big to fail, is really understanding the full population of these low surface brightness galaxies.
The latest paper on this argued that there is no dark matter in one.
I know, Peter and I were both at a symposium a few months ago honoring Sandy Faber, so I saw that strange object, and I will make the same comment in my talk as I made to him at the time when we get there. Okay, so we can, of course, model dark matter very well, and then we can ask questions about the shapes and distributions of dark matter halos, and we are most effective at testing those predictions really in the lowest mass and highest mass systems, which are dark matter dominated, so that baryonic stuff does not get in the way of our interpretation of the shapes of the dark matter halos. And today I really want to focus on the dwarf regime. Talk a little bit more about the UDGs from Peter in a little bit. But the point is, we have a plethora of small-scale challenges to lambda CDM that come from studies of these ultra-faint dwarf galaxies that are totally dark matter dominated. We may or may not be missing halos in an absolute sense, the missing satellite problem, but it seems very clear now, I think, that the observational shapes of dark matter halos do not match the predictions, and the related problem that, at least in the Milky Way, we seem to be missing the satellites with the highest rotation curve. So of course, it's a niggling question whether we can understand if you're too big to fail in the field really holds up if we don't have a complete census of low mass dwarf galaxies. And I believe that these pink dots are all H1 selected. And so with a survey like HSC, we have a very large volume. We can now start to find extraordinarily low surface brightness, dark matter dominated galaxies out to a couple hundred megaparsecs without relying on gas, and try to understand the full population of these low mass things.
What does too big to fail mean in astronomy?
So it took me a couple years to say this right, but the basic idea is you go into your dark matter simulation and you find Milky Way-like halos, and then you look at the rotation curves of the satellite population, and you compare them to the rotation curves of the real satellites in the Milky Way. And you see this strange thing that the the real systems do not cover the full range of rotation curves that you expect from your simulations, and specifically, you're missing the ones you would have thought were hardest to get rid of. They are too big to fail. So all the ways you think you might use reionization or early supernova blowout to get rid of some baryons in some of your satellites so that we're missing them, you'd think those would be hardest for the these most massive halos. This problem and this problem are closely coupled, because if you don't have the shapes of the dark matter halos right, then comparing the rotation curves is also a bit tricky. People have then said, okay, well maybe the problem is that we don't understand processing that happens when the satellites fall into a halo like the Milky Way, so let's actually look at dwarf galaxies in the field, where you can't use a bigger halo to mess up the baryon. So field populations are even better for these small-scale lambda CDM questions, and that's this H1 selected sample here. So I'm trying to make the case that we would like a complete census of very low mass dark matter dominated field galaxies that are not necessarily the most gas-rich things in the universe, just to see if it's the same population and see what we're missing. So that's my sort of argument for why it's worth spending a bunch of graduate student time to find these galaxies.
That little piece of jargon covers a lot of ground.
Yeah, I think I mainly said it right.
Thanks.
Thank you for asking. I shouldn't have gone so quickly. Okay, so like I said, our interest in this was really sparked by work that Van Dokkum and collaborators did with his small telephoto lenses, this Dragonfly survey, and this is Peter's previous favorite object, Dragonfly 44, that seems to have an incredibly rich globular cluster system, 10 to the 8-ish solar masses in stars, but apparently a Milky Way mass halo. Because he's Peter, he spent 33 hours with CACs to get a velocity dispersion. It seems like the stars are moving very quickly. You heard that he now has another UDG that perhaps has no dark matter at all. This sparked a search for more of these physically large but star-poor systems in a bunch of rich clusters and slightly less rich clusters. The beauty of a survey like HSC is that we are not going to start by looking around rich environments. We're just going to look everywhere and see what we find. Now, how do you make such extreme galaxies? There's sort of two pictures. If, in fact, you only find these things in rich environments, then you can imagine that they started their life as a proto-Milky Way with lots of gas and lost it by processing in the cluster environment. And you can imagine that these things that you find in rich clusters will only stay bound, there are so few stars, if, in fact, they live in very massive halos. So that story all seems internally consistent, but you also do expect some tail of very large, very low surface brightness galaxies, just because dark matter halos have a range of angular momenta, and the high spin tail will give you very physically extended galaxies. This was Julianne Delcante's thesis, and she actually went out and looked for low surface brightness galaxies in the 90s, and she found them in support of her theoretical work. I know that Avi and others have since elaborated on this picture with an eye to the sort of UDG-like things. So again, you really want a sample of galaxies that is not super biased towards these rich environments, so you can try to disentangle which of these formation channels is most important for the majority of galaxies. So Johnny set out to use HSC to find low surface brightness galaxies. Here's Johnny, and here is just some of his most beautiful systems. We found about 800 galaxies in the first 200 square degrees of the survey. So under here is a 27 magnitude per square arcsecond galaxy, which is real. This guy is also one of our faintest. They're just super beautiful and fun, and of course, the comparison, the obligatory comparison with Sloan. So a very small number of them were in fact detected by the Sloan pipeline, but mostly not, and you certainly could not measure their properties. So we really are in a new regime as far as large volume imaging surveys. This is just a summary of their properties. So they are bimodal in terms of color. About 50% of them seem to be totally red, and the other half are blue. So the UDG colors live right in here, sort of typical red guys. Here's our surface brightness limit, okay. We were actually selecting, this is a technical detail, but we were selecting on effective surface brightness rather than central because a small fraction of them have very, very bright nuclei, and we did not want to lose those. So that's another super cool and puzzling aspect of that dark matter free thing, is it has a whole bunch of very luminous clusters, and we have a really rich data set to study such clusters in these data. Super interesting, and we think real characteristic of the data is that the red guys have a much, much broader distribution of surface brightness than the blue ones. And so if this is real, it seems to be saying that there is a limit on the density at which you can form stars. So that could be quite fascinating if it turns out to be real. Johnny's last thesis chapter is to understand his incompleteness well enough to determine if we're somehow biased against the blue things at low surface brightness. Also interesting, Peter emphasizes this as well. The green line here is the distribution of axis ratios you would expect for disks. And our guys, both the blue ones and the red ones, are significantly rounder than that. So they are really puffy systems. Even the ones that are actively forming stars are quite round. Here's just the standard size versus mass plane. Here's where your high surface brightness galaxies live. Those diamonds are your Malin 1 type. These are low surface brightness disks with a high surface brightness bulgy core. And then the red is the UDGs from Coma, and these are all the objects for which we have some sort of distance. A couple because they were associated with a supernova, a couple because they were detected in alfalfa with Arecibo, and then this is a relatively rich group at low 15 megaparsecs away, so we have a bunch of standard dwarf elliptical type things, and then a bunch of these UDG things that are bigger and more massive, and a few kind of bulgier Malin 1 type things as well.
Just a quick question. The
Yeah.
lack of the blue systems in Coma, is that just a reflection of this?
There are no
layer in the
blue
cluster?
gassy things in clusters, yeah. It's an interesting question. The reverse question is the one where the kind of the money is, right? Is do we have red things that are totally isolated? Because then you have the real challenge of shutting them off without a rich environment to do it. And the H1 surveys would never find those. So that's one of our sweet spots.
But it seems like you have found.
So we don't know whether we have red isolated things yet, because we don't know the distances for most of our systems. This is just one piece of the HSC survey, so you can automatically already see that there are overdensities. Some of our things are harbored in large-ish groups. Up in the corner is one of those. And then some that are perhaps isolated. We just, from a cross-correlation analysis, we can say that the majority of the objects are within 20 and 200 megaparsecs. That's not surprising, because physically their sizes on the sky range from 2 to 20 arc seconds, and they'd start to get extraordinarily big if we went much beyond 200 megaparsecs, but that's their statistical distance distribution. So ranging in stellar mass from 10 to the 7 to 10 to the 8, and in size from 1.5 to 6 kiloparsecs, basically. We are starting to get direct distances now. This was a Gemini fast turnaround targeting a couple of the sources that are brightest in Galax. So nearly all of our blue things are Galax detected, so actively forming stars. And we actually, these things are 24.5 magnitudes per square arc second, so we didn't know if we would be able to easily detect emission, but in fact we were very easily able to detect H alpha. And so this is multiple slit positions now. In particular, this guy, very well spatially resolved even in Galax. So this gives us physical properties for these guys, and that's where they live, sort of at the small end of the UDGs. This is also in the context of local volume dwarf galaxies. WLM is right outside the, I don't know, 2 megaparsecs from the Milky Way or something like that. So you can see how these compare to something like Fornax, and then how they compare to typical UDGs as well. We're also able to say a little bit about their gas phase metallicities, which is kind of fun. So on the left, I'm showing the standard Baldwin-Phillips-Turlovich type relations, looking at the strong ratios of the strong emission lines, which tells us what is ionizing the gas. So that dashed line, everything below it is photoionized by O stars, and the gray circles are typical dwarf galaxies in Sloan, and the blue and the red are sort of summed apertures for our two guys. And the kind of interesting thing is if you just naively take nitrogen 2 to H alpha and turn it into a gas phase metallicity, they seem to lie somewhat high for their stellar masses. So maybe that's real, or maybe that's telling us that actually there's much more diffuse gas far from the O2 or from the H2 regions, and so the line ratios may be fooling us, but this is sort of an interesting, not terribly significant result.
Jenny?
Yeah.
So the two red points there, maybe over the AGN region. Is there any evidence at all that these galaxies might have AGN?
I always get asked whether there are black holes in these galaxies, and I would love to know, but I think it's really fully consistent with star formation, and the error bars are really large. And there's a lot of junk from sky subtraction over there in the red. So we really need a bigger sample, but it's at least fully consistent with star formation at this point. We thought about putting in a Chandra proposal, but I lost my nerve, so we didn't do that. We'd have to look at an awful lot of them before we had any chance of finding and accreting one, even if they all have black holes. All right, so I showed you in the two-dimensional spectra that we do have some spatial information for this guy. So, million-dollar question is, what sort of dark matter halos do these very diffuse galaxies live in? So the green points are the rotation curve. We think the stellar mass is 10 to the 7 from SED modeling, which I'm not showing you here, all the way through Y. So we actually have really good photometric constraints. And then just a handful of other local volume dwarfs for which we have really good rotation curves ranging in stellar mass, again, from 10 to the 7 to 10 to the 8. And the punchline, although we did not do detailed modeling, is that this thing is consistent with having a typical dwarf halo mass. So not an extreme Dragonfly 44 type thing, but less than 10 to the 11 solar masses in the halo.
How do you get the mass of the halo if you're seeing only the enough after all?
Well, so we see H alpha as far out as we see stars,
Okay.
which is, it's very large on the sky. So it's 6 or 7 kiloparsecs.
Yeah, but that's because it's close to us. The fact that it's larger in the sky doesn't matter.
Well, 7 kiloparsecs is big for a 10 to the 7 solar mass galaxy. So it's true that we don't know whether the rotation curve has flattened out. So we're,
Right.
You
don't know the virial radius. That's
but
the thing.
we're just qualitatively comparing to other typical dwarfs, and the rotation curves are not different. So it would have to rise dramatically at larger radius.
No, it's not so much how much it rises, it's how far does it go in terms of the virial radius. What's the extent of the halo?
Right, which
Because
we don't know.
That's right. So if the rotation curve is flat, the question is, how far does it go?
And I wouldn't even claim we know if we've reached the flat part of the rotation curve. I'm not trying to make a super strong claim, but we don't see very high rotation within 7 kiloparsecs or wherever we extend, which you might already do if this was in fact a Milky Way mass halo. I'm pretty sure it would be higher than 40 kilometers per second at these radii if it were a standard shaped dark matter halo that had a Milky Way mass. So I think we could be more careful, and I think we could rule out Milky Way. So that's the extent of the claim we're willing to make. It would be very nice to have two-dimensional data. It would be nice to spectrally resolve the H-alpha. These are all things that we can do now that we know we can detect it. Our main goal with these spectra was just to get a redshift, so we're kind of pushing a little harder than we expected to. All right, so that's everything that I wanted to say about these low surface brightness galaxies for now. We have 800 of them in 200 square degrees of HSC. We know that they live in a wide range of environments. I should have said these guys, based on their redshifts, are actually both quite isolated. Their nearest sort of Milky Way-like friend, I think Johnny's cut was 2 times 10 to the 10, are all more than 3 megaparsecs away. So not shocking because they're forming stars, but at least we are indeed finding truly isolated low surface brightness galaxies this way. From cross-correlation, we know they live 20 to 300 megaparsecs from us typically, and all the blue guys are detected in Galax, and we now have just a couple in this pilot where we're actually able to measure rotation curves and gas phase metallicities, and so that'll, I think, become easier as we learn how to do it. So I'll pause and see if there's any other questions on this bit before I go on to the.
Do you have a plan to get the distances for the red ones?
So I had this really great plan called JWST.
It's still in effect, just delayed, that's all.
Because we would be able to do tip of the red giant branch out to 90 megaparsecs actually in not much more than a couple hours, which was sort of blowing my mind, and I was super excited. I know, except for not so much. Other plans, so obviously the cross correlation gives us statistically the distances, and we are going to get continuum spectra and get redshifts for some of the red ones. So we've been playing this game of, can we guess which ones are most likely to be isolated based on their most likely friends, and then really trying to target those first. But that's where we are. No. I mean, well, the things that have been done with COMA, both by Peter's group with Keck, but also by Zveritsky, you can get the break in a couple hours or less. You just need a very, very large slit, so you get as much light as you possibly can. So you can play that game at least to 25th. So this was, JWST was going to be how we targeted the 26, 27 magnitude per square arc second things. There's, of course, the question of what we can do from the HSC data itself, because there's surface brightness fluctuations and semi-resolvedness things you might do for the ones that are really close. We've been too intellectually lazy to try that yet, but I think that's the next thing to do. Yeah.
I'm trying to understand that kind of punchline then. So you have these 2 isolated galaxies, so it's not gas stripping in some dense environment.
Well, but those are blue, so
and
it wasn't
blue,
shocking
so
that they're
gas anyway.
right.
And so why are they so different from a Milky Way galaxy in terms of the very low stellar masses? They just have, for some reason, had highly efficient star formation over the last 13 billion years.
Well, they're not necessarily terribly different from other dwarf galaxies of their mass. They're just
But they're much larger.
perhaps, yeah, they're larger. They're
So something is different, right? Either
right,
they're larger
so,
for a dwarf galaxy or they're low mass for a Milky Way type.
right. So I tried to argue that they probably don't live in Milky Way mass halos based on this 40 kilometer per second velocities that we see. So presumably the easiest way to arrange them to be low surface brightness is that they have more angular momentum. But the real punchline is to figure out our incompleteness and actually use the larger volume. So, pretty much existing surveys are either within the local volume, so 4 or 5 megaparsecs, or they're H1 selected. So we would really like to understand our incompleteness and then revisit these too big to fail type questions with a complete sample, and this is just the beginning stages of that.
Is the resolution of the data too low to get a handle on the global classic populations?
Again, we really could do better. There are clearly some fraction of them, 30%, are clearly nucleated, so we would get lots of nice information about their nuclear star clusters. And then the blue ones are very clumpy, but those are probably H2 regions, so we really need to just start finding all the point sources and looking at their colors and figuring out in what cases are they globulars, in what cases are they H2 regions, in which cases are they red giant branch stars and AGB stars. We did get some HST time to look at the globular cluster populations and some poor group ones that we have. But I'm pretty confident we can play that game with some fraction of them just with HSC, but again, we haven't done that yet.
I guess statistically something could be said, but it's a difficult game.
Yeah, I think that's right. It's just, you know, almost certainly in a few cases those are going to be individual stars, and the RGB stars and the globulars are going to have similar colors. So, and you know, it's really deep data, so we really have to understand the background galaxy point source population pretty well and get rid of that, which I think colors will do. So, there's definitely more to do, and we haven't. Yeah.
Anyway, which fraction of the sky, if you were to integrate this population all the way to redshift 1 or 2, which fraction of the sky do you think is covered by these guys?
They're still pretty rare, at least if we're
the
not.
number density relative to galaxies, like the Milky Way, and how much smaller is it?
Oh boy, I don't know the answer to that. That's a good question.
It's an interesting question to ask
Yeah.
whether the surface brightness of the sky is affected by overlapping these events.
Right. Yeah, that is an interesting question. I don't know the answer. I think our incompleteness is such that probably that at least the number densities are flat between 25 and 27. If not, still rising at 27, but it gets super, super incomplete down there. And presumably that's how faint you have to go before you start to think they were here in the sky somehow. That's a good question. So back to this question of ways you can make dark matter-free galaxies. One of the first papers Johnny wrote when he was trying to understand his search algorithm was about this little fluffy thing up here, which I think you can actually see because you have an awesome projector. It's extremely large on the sky and seems to be spatially associated with this clear merger remnant here, which is a galaxy at redshift 0.04, has a nice, beautiful caustic from some recent merger, and so we sent this around to all of our collaborators, and half of them said, oh, that's a foreground, you know, local volume dwarf galaxy, and the other half said, oh, it's clearly associated with this galaxy. And so we wrote a quick paper on how challenging it can be when you push into these kinds of surface brightnesses to figure out whether you're seeing tidal fluff or you're seeing galaxies. So I do still wonder whether Peter's dark matter-free thing is actually a galaxy. He says it's very round, and that's fine, but we stared at a bunch of Katherine Johnston simulations to try and match this sumo puff, as we call it. And you know, you can get all kinds of fluffy things if you've had a merger and it leaves tidal debris. So for us, this is a kind of major astrophysical contaminant, is when do we think we're seeing leftover tidal things which are not bound galaxies, and when do we think we're finding real galaxies. And I was showing this to one of our perspectives last year, Erin, and I told her a really fun project was going to be to look intentionally for tidal features with HSC, and she said, I'm coming to Princeton to do that with you. Yes.
To follow up on that, so is the way to actually tell you have to resolve the full tidal stream? I mean, in principle, you only see the brightest patch.
The velocity Velocity distribution.
Wow. I mean, first you would just like to get a redshift. I think that would go a long way towards telling you whether it's associated with this galaxy. And if it's associated with this galaxy, then it is, I think, most likely to be tidal. Although even then, the geometry relative to the caustic is kind of funky. We also tried to play some games and go deeper to see whether there was actually a bridge between the two, and that was totally inconclusive. Yeah.
So if that was a tidal stream, you would have expected it to also strip off some of the Galapagos cluster population? Because that's how they found like the velocity dispersions in that new.
I know, and it has a ridiculously large number of these bright clusters, right? So, yeah. Yeah, but it's like, we have one of those in the Milky Way, right? It's like Omega Sun-like, isn't it?
Yeah.
Yeah. So, I mean, maybe you could have made those in the merger, I guess, but I don't know if that's plausible. And I don't know if they know whether there's H1 associated with that thing. That was Jacqueline's question. We also have been asked many times if there's H1 associated with this thing, but we haven't actually looked yet. Okay, so even talking too fast, I'm definitely going to run out of time. But let me transition then to the search for tidal features. This is work led by Aaron. And so you can imagine a bunch of things you can do if you get a big sample of tidal features around galaxies. The first obvious one is try to say something about the merger histories of the galaxies. It quickly became clear to us that pair counting of various sorts will always win because you can understand your completeness a whole lot better. So let's take that off the table as an interesting question. Then the sort of richer morphological information in the tidal features tells you something about a combination of the distribution of mass ratios, the distribution of infall energies, and the halo shapes that led to the tidal features that you observe. And so the end game is, of course, with an eye to something like LSST, is how can we automatically find and then classify the morphologies of these tidal features, and we're just making first attempts. So first of all, it's typical in the literature to separate these into shells, where you have these clear caustics, and those are the kinds of tidal features you get when you have the satellite coming on a radial orbit, so everybody has the same turnaround radius, and streams, which you get when you just tidally strip a small galaxy. So Dave Hendel has been thinking on the theoretical side about how to use the number of shells versus streams in comparison with cosmological simulations to understand something about the infall distributions of satellites. You can also think about shells in particular and what they might tell you about mass ratios for mergers. This is work done here by Roxana Popp with Illustris, and they had this really fascinating result that all the shells that she picked out of Illustris seem to be remnants of major mergers. And so in that case, you then expect the stars out in those shells to have very similar colors to the central remnant galaxy. So this is eminently testable with our data. So that's just a flavor of the kinds of questions that we can test with large samples of tidal features. We decided to start simple with known galaxies with SDSS spectrum. Okay, so the parent sample here is in gray. Mostly it's legacy Sloan, and then BOSS kicks in at the high redshift end here. We're almost completely incomplete above redshift 0.2, 0.3, so most of what I'll say is redshifts below 0.2. And then the black are all the tidal features that Erin has identified, and then there's still some contamination that her algorithm was not yet able to remove. I'm not going to go through the details of what she's doing, but it's basically like unsharp masking. So she's removing the smooth components of the image and picking up the high frequency stuff. So if you had a tidal feature that was like the sumo puff and was completely smooth, we would not find it. But in all the simulations she did, she got a bunch of simulated tidal features from David Hendel and did a bunch of recovery tests. Almost everything has some sort of caustic or stream that's high frequency enough to be detected. And so we're really pretty complete down to 26.5 magnitudes per square arc second. Here's just some examples of the kinds of things that we're finding. So nice examples of shells, streams, and galaxies with no tidal features at all. Here is a summary of the sort of macroscopic properties of the two samples. So the red are the shells and the blue are the streams. And you can sort of automatically see, and this is not super surprising, but the shells tend to live in the most massive galaxies, whereas we're seeing streams in around lower mass systems. The shells live in the reddest galaxies, and the shells live in the most centrally concentrated, so the big ellipticals. And indeed, we see a very clear trend towards higher and higher shell fractions in more massive galaxies. Again, this is what you expect because you have more radial infalls from satellites. But what's fun is that because we have 1,200 tidal features now, this is really the largest sample to date, and it's only the first 200 square degrees of HSC, we can take a window in mass where we have a significant sample of spirals and compare the shell fractions around the spirals and ellipticals at fixed stellar mass, and we find far, far fewer shells around spirals. So that's just kind of fun, and so it tells us that it's not just the mass of the system that's determining whether or not you get these shells. Probably the infalling satellites around spirals are much lower mass, and so if we were 2 magnitudes fainter, we would start to find the shells, but we don't see them because we're picking up only more massive things.
So what is the fraction relative to the total, rather than normalized by?
The overall detection fraction is 17% over the whole survey, and then it's higher for streams because they're higher surface brightness, and it's lower for shells. And this is exactly a function of how deep you go, right? So if you do the game of really going to 28 or 29 magnitudes per square arc second deep around targeted big galaxies, you can get 80 or 90% tidal feature fractions, right? Because you just, merging is happening all the time. So it's just a question of surface brightness limits. But we can ask some interesting questions. So now the next clue that we have about the mass ratio in particular comes from the color of the tidal feature. So these are histograms for the shells and the streams of the difference in color between the tidal feature and the central galaxy. And what you see is, let's just look at the shells first. So all shells, and then the shells around the most centrally concentrated galaxies. Almost all of them, the peak color difference is around -0.2, and we can just use the fact that elliptical galaxies live on the red sequence to turn that color difference into a mass ratio. It corresponds to about a 4-to-1 merger, although the error bar in that is obviously very large. So this is sort of a minor but not so minor merger. And then interestingly, there is a tail of things that are as red or redder than the central galaxy that I'll get back to in a second. The streams are a little bit bluer on average, but then there's a long tail of things that are currently still forming stars. This is not surprising. These are spirals and ongoing mergers that do have gas and star formation. So just zooming in on these reddest tidal features, very interestingly, they are all these type 1 shells, where the shells are stacked along the major axis of the galaxy. This is exactly what you would expect if you made your shells in a major merger. So Aaron and I call these the pop shells. This is exactly what you would have expected if indeed a major merger was the progenitor of these things.
By the way,
Yeah.
the same phenomena should also take place in clusters of galaxies, groups of galaxies, because they also are associated with mergers. And the question is whether that would lead to some misidentification of these, the first topic that we discussed.
Yeah, so I was wondering whether you could make a lot of the COMA UDGs with tidal stuff, right? I mean, obviously that's something we've been thinking about. They just wouldn't last long, so you'd have to be regenerating them all the time. Plus, I don't think there's a lot of mergers in clusters, right? Because the galaxies are moving too fast. So there's a lot of harassment, but there's not a lot of mergers. So it's not clear to me that you can, I suspect that most of the things in COMA are in fact bound, but that's not a quantitative statement. But yeah.
Do you see any dynamical links between dwarf galaxies suggesting they might originate from the same event? If they're coming from, say, bits of the tidal tails, you might suspect that several of them would come from a single merger because potentially that they would live in phase space in a similar region.
I don't have any dynamical information for the vast majority of our dwarfy things. But certainly with infinite telescope time, I could try to follow them up and figure that out. First, we're just going to ask whether they're mostly in the halos of other galaxies or mostly isolated, and then I think we can get into those second order questions. Okay, so that's all we have to say so far about our tidal feature sample. So it's about 17% of these massive SDSS galaxies that we're able to find tidal features down to 26.5 magnitudes per square arcsecond. As expected, we find shells around, more elliptical-y galaxies, but we definitely see a dearth around spirals at fixed mass. Most of the shells are bluer than their galaxies, except for this tail of red things that may actually have major mergers as their progenitors. So given the time, I think I will skip the AGN question for now and just take questions, but I can show you the main punchline slide for that if you guys want
to. So we can take questions, or I don't know. We do have time, Jenny, if you wanted to.
We can see the punchline.
See the punchline.
You want to see the punchline?
Yeah.
Okay. So the age-old AGN question is, do you need mergers to drive AGN activity? A tremendous amount of work has been done locally for low luminosity things where it's very, very clear that lots and lots of different physical mechanisms can trigger AGN activity. The bigger question has remained whether for the very most luminous sources you require a galaxy-wide disturbance like a major merger. The theorists don't have any better ideas, and so we've always sort of assumed that if you get to a high enough luminosity, you need a merger to trigger. But people at AGN meetings, even to this day, come to blows over this question, with people like Carolyn Villeforth creating matched samples of AGN and mass-matched inactive galaxies and claiming exactly the same merger fractions in those two populations. And people like Elad Glickman claiming that if you take the most luminous quasars in the universe, all of them, 80% or more, live in merger hosts, which you could not do randomly at any stellar mass. And so there's, of course, lots of horrible details in here, like Elad is selecting red things, and so maybe red things, dusty things, more likely to be in mergers. Carolyn's selecting blue things. So we thought we could make a contribution with HSC, and just to skip to the punchline. Where's the punchline? So Andy did a fancy decision tree thing to find mergers. Here they are. So lots of beautiful mergers in HSC. And the punchline is that the non-interacting galaxies, this is their merger fraction. So this is as a function of stellar mass. What fraction of the galaxies harbor AGN? So these are non-mergers, and this is their AGN fraction, and then these are the merger galaxies. And so galaxy mergers are almost a factor of 7 at the highest redshift bin more likely to contain an obscured AGN. So we can, and at lower luminosity, you see a boost in AGN activity at the sort of 30% level. At these luminosities, merger activity boosts AGN activity by a very large fraction. So that's the punchline. We are still not answering the absolute question of whether you absolutely require a merger to trigger an AGN, but it's clear that mergers play a significant role in triggering luminous quasar activity at these redshifts. All right, you can clap for me again.
So, Jake, the question about the survey overall. So it's an incredibly rich data set. It's, you just started
Yeah.
going through it. What's the plan for
Public data release.
releases, if there is one?
Yeah, so there has been a public data release already of the first 100 and something square degrees, including all of the pipeline products, just like you're used to with Sloan. So there's a bunch of shape measurements and things like that. We are actively fighting in the collaboration now about when the next public data release should be, with a discussion. I mean, we're sort of, the error bar is like 4 months. Should we wait till this or that proposal deadline before we release it to the world? And I think that one will be 500, 600 square degrees, something like that. So basically, 6 months to a year after each major code update is when we're releasing the next batch of data. And believe me, you are happy that people like Johnny are sifting through the problems with the database and not you guys.
And there's a time domain component to the
Yes,
area,
so
or just
the 30 square degree deep component has a high redshift supernova surge component, and the cadence is, I think, the highest cadence data are being taken for G and I, with you wanting to go as blue as possible. And I think it's something, it's not even every month, but it's, a few epochs per year. So we thought a little bit, for instance, about whether it would be interesting for TDEs, and I thought not so interesting. I frankly have not paid a lot of attention to those data, partially because for the first year and change, we were so desperate to get some weak lensing results first that almost all the data were wide, and then I got distracted by all these things, and so the time domain things are going now, and I don't really know the status. I also we have a group at Princeton now thinking a lot about stars in the Milky Way and streams and things like that. So that's a whole other super rich component of the HSC data that we're just starting to think about.
Any more questions? No? Well, Jenny's going to be giving another talk at the ITC luncheon. Let's give Jenny one more round of applause.
Well, this very, very red shells are kind of interesting. Yeah, we have some. Yeah, we have some. Yeah.
Suggest if it was a major
Suggest it was a major.
But it's
I
not.
can't imagine that had anything to do with major neutron star merger. But
Unless we start seeing all the galaxies.
yeah, yeah.
Otherwise, yeah, I'm doing.
Oh, thank you. I did want to ask you very quickly, because one of the things I'm super excited about right now, and probably should